Just wait a minute. Okay. So, hello everyone. Welcome to the second online workshop on arterial coordination signal control, jointly organized by 62 of the WCTRS and the Tongji WCTRS Water Transport Research Center. I'm Keshuang Tang from Tongji University. First of all, I'd like to ask for your kind cooperation in keeping your PC or cell phone with mute mode during all the presentations. And of course, you can turn it off during the Q&A time. Thank you very much. Since some participants may not be aware of SIG-C2, so I want to briefly introduce our SIG. The SIG-C2 is one of the special interest groups under the topic area C of WCTRS. The focus of this SIG is urban transport operations. Currently, I'm chairing this SIG along with Professor Zong Tian from University of Nevada at Reno, who is also the manager of topic area C, and Dr. Atsusa Toriumi from University of Tokyo, who will be moderating today's workshop later. So far, SIG-C2 has 40 members from 18 countries. For more details about WCTRS and our SIG, you are welcome to visit the below website. So before the start of the workshop, I would like to shortly explain the background and objective of this workshop. So in the year of 2017, WCTRS and elsewhere decided to publish a co-branded book series. So in this context, SIG-C2 planned 3 books on global practices on road traffic signal control. So far, the first book has been published already, and now it is online. It is available to purchase at the website of Elsevier. The second book will focus on arterial coordination and accurate control. Now, an auditory team led by Professor Zong Tian is working on it, and they just submitted the book proposal to Elsevier. The third book will be about accurate and adaptive control in the context of emerging technologies. This book is still in planning stage, and you are welcome to contact me if you are willing to contribute to this book. To better prepare for the second book on arterial coordination signal control, we planned this online workshop series. So the primary objective of this workshop is to invite different professionals from academia field and industry side to share the state-of-the-art practices in their countries, and so that we can discuss the differences among these selected countries. Then we can have a global picture about arterial coordination signal control. So this is a general purpose of this workshop series. On December 11th, in the year of 2020, we had the first workshop in which 5 professionals from USA, Germany, Switzerland, and China, respectively, shared their experience and insights. This workshop attracted nearly 100 participants from all over the world. I would think it was quite successful. And the recorded video and presenters' slides are now available at the website of SIG-C2, as you can see here on the right. Please note that a password is required to open these files. Today we are having the second workshop in which practices in Japan, Netherlands, and Australia will be introduced and discussed. The third workshop will take place in March in 2021. The topic of this workshop will be latest research and practices in the context of emerging technologies such as connected vehicles and autonomous driving. So this is the agenda of today's workshop. We are very honored to have 3 professionals from Japan, Netherlands, and Australia to share with us about the latest development on arterial coordination signal control in their countries. The first speaker is Professor Takashi Oguchi from the University of Tokyo. His main research topics include signal control, traffic flow theory, and intelligent driving. He currently serves as the director of ITS Center at the Institute of Industry Science of the University of Tokyo. He has been doing research in the field of traffic engineering for more than 30 years and has led many national level research projects, such as the Strategical Innovation Program of Japanese government on autonomous driving and traffic signal control guideline revision of Japan Society of Traffic Engineers. I think he's the most appropriate person to introduce the practices in Japan. The second speaker is Dr. Marina Solomonos from TU Delft, and her main research topics are urban intersection control, design of intersections and roundabouts, and traffic management and control for cyclists. In her talk, he will explain signal coordination in the Netherlands, the various methodologies that are applied for both common traffic signals as for the intelligent traffic signals that are being installed currently. The policy on when to coordinate is explained, how traffic users are informed, like speed advice, and also the coordination for cyclists will be illustrated. The third speaker, Mr. Daniel Silt, is from industry side. He is the chief consultant of Transmax company in Australia. Daniel has been working in the field of traffic engineering, coordination, and management for more than 18 years. He has extensive experience successfully working with road authorities, including traffic management centers, providing both strategic and operational leadership. As a principal consultant with Transmax, Daniel plays a very fundamental role in contributing to the delivery of cost-effective and fit-for-purpose ITS solutions. So for each presenter, we are going to have 30 minutes in which presenter can finish their presentations within 20 to 25 minutes. And we will leave 5 to 10 minutes for short questions right after each presentation. Then at the end, we are going to have 60 minutes for specific questions and general questions and comments. So this is the agenda of today's workshop. So on behalf of 62, I would like to thank all the three speakers for sharing your experience, researches, and insights, and thank all the audience for attending this workshop. I believe this workshop will be an informative and useful event for you. Okay, so I will stop my screen sharing and invite my colleague, Dr. Azusa Tolibumi, to moderate the workshop. Azusa, are you there?
Yes.
Okay, Azusa, please. Thank you.
Yes, thank you. Yeah. For everyone, thank you for attending again to this workshop. I'm Azusa Toriumi, as introduced by Professor Tan. So let me start the workshop. And before that, I would like to remind that you can have questions, ask questions, either right on the chat function in Zoom, or after each presentation, we are going to have a Q&A session, so you can unmute your microphone and ask the questions directly to presenters. Yeah, thank you. So first, let me invite Professor Takashi Oguchi from the University of Tokyo to introduce signal coordination control practices in Japan. So please start your presentation.
Okay. Let me try to share my screen.
Okay, it works.
Okay. Oh, sorry.
Another one?
No. Like this. Okay.
Okay.
All right. Thank you for your participants and kind introduction of me. I'm presenting the practice in Japan for signal coordination. My name is Takashi Oguchi from the University of Tokyo. And as Kishan kindly introduced me, I'm now leading so-called Advanced Mobility Research Center in my institution. This is the Institute of Industrial Science of the University of Tokyo. And 1 year and a half ago, we also start to organize a new organization, so-called Mobility Innovation Collaborative Research Organization. It's a cross-disciplinary organization across whole the University of Tokyo. We are now starting this kind of activities. And for today, as also Kesha mentioned, that I'm a bit busy with the project, national projects, and just try to summarize the Japanese practices in the signal coordination. And so firstly, I try to explain about the Japanese history on the introduction of the coordination control. And maybe in Japanese situations, the responsive control with the signal coordination is very common. So I'll also talk about that. And secondly, I'll try to explain the practices in Japan and the background theory. Actually, this is brought by my lecture slides. And the third one is also from my lecture, the signal coordination, and try to enhance to the idea to the area-wide control. And fourth one is some application provided by the Japanese industries and also applied with the Japanese police agencies. Actually, in Japan, signal control is responsibility of the police agencies for each prefectures. And the national general rule is provided by the National Police Agency. Okay, firstly, for today's my talk, I try to read out, check the one history book. This is my first time to checking detail of this book, so-called Traffic Signal 50-year history. And I was very surprised that the first introduction of the signal coordination control in Japan is at Tokyo and was on 1933. And the concept is very simple, that give this kind of signboard at the traffic signal with the 32 kilometers per hour. So try to announce to the drivers who try to keep the speed of this speed level. Then the driver can catch the next green. So this and also try to give some timers with some DC circuit system. And this is applied for one line, one arterial with 15 intersections. And afterward, even before the World War, such kind of cable systems is rather difficult for installation. So they just after 3 years, they changed to uncabled coordination with the synchronized clock. And in 1940, before starting the war, they already had more than 100 intersections of this kind of a coordination system. And after the World War II, maybe such kind of a technical application was stopped and suspended. But in 1953, a kind of a semi-actuated coordination control was started again in Tokyo. Which means the cycle length cannot be fixed. It could be changed. And 1963, it is a kind of a national project. And they make a first trial of installation of traffic actuated signal coordination system. So set the detectors, and the 18 intersections have a traffic controller. and ruled by the main computer. And the idea is giving the set of parameters of the signal cycles and splits and offsets, and combining there are 120 patterns, and try to select the patterns. And then with the three, after have experience of the 3 years, in 1966, a first trial of the area-wide signal coordination. So at the Ginza area, this is the heart of Tokyo, actually the commercial heart of Tokyo, and the 35 intersections applied for this kind of trial. So not only the one arterial, but a kind of a network-wide applications. And introduced us a very fundamental idea to this system. And then rather full-scale the application started in 1970. This is the original form of the Japanese centralized traffic control system. And so this Ginza area is included here, and rather widened area application. This is the start of the Japanese history, I think, up to these days, today. This slide explaining about some technical manual, the background for such a practices. So the first manual on the signal control was published in 1969. And also a kind of a design manual of the intersection, a geometric design manual or plan also started. And it's parallelly published under different timelines. And in 1983, this is the first version of the so-called traffic signal control manual. Already rather detailed description related on the coordination is included, was included. And in 1994, we have the revised versions. And a kind of established idea of the pattern selection of the coordinations included. 2006, revised versions, including some, not parameter selections, but the real-time calculation methodology is also included. And very recently, we had the unified, comprehensive basic manual on the intersection plan design and the operations. Okay, so I also introduced the Japanese situation at this moment. So this number is also introduced in the first published book by WCTRS, as Keisha mentioned. And we had centralized traffic control centers. Basically, every prefecture in Japan, we have 47 prefectures, had a head of centers and some control centers, or also have some subset of the center in large cities. So a total number comes to be 168. And yes, as I mentioned, National Police Agency is have a responsibility on this. And any of those centers, main machines and systems are provided by these 5 Japanese industries. And the talk about the number of signals applied such a coordination. Okay, the more than 70,000 signals, intersections are connected to such a traffic control center and also have a coordination function. On the other hand, around 26,000 have a coordination functions, but they unconnected. Therefore, independently working and they set the coordinations. And the 900 push button is also connected to the coordinated. On the other hand, we had a rather large number of the isolated signals. Some of the major, our topic is try to connect those isolated signals with the 5G connection technology. All right. And so for the coordination, we had a very general simplified idea of the coordinations and with the centralized control system. So to consider about the area-wide road network, we separate into the several subnetworks. And sometimes a group of the subnetwork is having a same cycle length. Then try to connect the elements of the subnetwork and they form the group of the subnetworks. So maybe you may see this is not so big subnet, but if you look at this area, this is a rather large subnetwork having the common cycle length 110. So maybe such kind of formation of the group of the subnets is one idea, having the common cycle length. And then determine the signal coordination for those intersections. So when you look at the intersections having one link connected with the different subnet, then we don't consider anything considered for the coordination between those two signals. That's the practices in Japan. So as you may also, maybe you are a specialist, that you may understood that the link length is one parameter to set the coordination offsets value, and the signal time is also important, and the some vehicle speed should be determined. Okay, so our Japanese application is very simple for this considering about the coordination, that the consider the one arterials having the simultaneous start of the green time for both directions, even for having the different phasing systems, and focusing on the one arterial and try to set the cycle length, and of course have some appropriate green split, and the coordination point of view try to set the offset values, which could be explained by the percentage to the cycle length in general. Sorry. Okay. And for determination of the cycle length in Japan, maybe one typical feature of the Japanese signal control system is try to adjust cycle length every time, very frequently, and with the 1 second resolutions, as I showed, 101 second cycle length or something like that. And for the coordination point of view, the cycle length is determined at the critical intersection, which means the rather very busy intersections which should accommodate the traffic demand at the highest capacity level, so that avoiding the traffic conditions. So with such a high demand intersection, we should provide rather larger the cycle lengths. So the other intersections not critical in the same group of the subnet should apply the same cycle length as a common cycle. And yes, okay, this is for just brought from my lecture note. So basically, our Japanese practice is based on the concept of the flow ratio, demand flow ratio to the saturation flow rate is so-called a flow ratio, and applying the flow ratio value to select the green split value. This is a basic idea of the setting the green split. So for the even for the coordinated signals, also we apply the same idea basically. This slide is just explaining about the classification of the different aspects. First, the classification aspect is a spatial idea. So isolated or arterial and network. And for arterial coordination or network coordination, coordination is one important topic to determine the offset value. On the other hand, for control classification, is a pre-timed control or responsive control. Those two major differences we have. So as I mentioned, that the signal is intersection which connected to the traffic center, control center, then a kind of a responsive control applied. And they basically even as I mentioned, so 168 traffic control center we have. But the majority is still kind of a simplified the macroscopic traffic responsive control applied, and which means the predetermined some patterns of the parameters are just selected with the some detector information. And rather a few number of the application of the some program formation, which means the real-time calculation of the parameters. And so multi-program pretimes means the okay for the different day of weeks or some special conditions. We have a predetermined the cycle lengths, green split, and the offset values. And so such kind of predetermined coordination control applied at around 26,000, as I mentioned, and plus the less than 1,000 push button pedestrian crossing. For the responsive control, as I mentioned, that the control parameters, cycle lengths, green split, and offsets are selected or real-time calculated, and using the detector information. And for just consider about the responsive control, it is rather popular for the microscopic response, which means each intersections have a function of the responsive control. For example, right turn vehicles detection, and then extend the right turn phase or give a right of way for right turners or something like that. And on the other hand, from the coordination point of view, some macroscopic responsive control idea is also comes to be applied in Japan. So yes, selection or generation of cycle split offsets. And also for the oversaturation situations, we had also algorithms for select those parameters or generate the parameters. Actually, to tell the history of Japan, the reason why we started to introduce the traffic control center in the heart of Tokyo, Ginza, was to try to alleviate the traffic congestions. So the control system in Japan, basically, the development of the control system in Japan is basically pushed by such serious congestion issues. At this moment, more than 70,000 intersections are controlled with this macroscopic responsive control scheme. Okay, this is just a textbook telling story. For one-way street, okay, the coordination is very easy. But for two ways, okay, if give the right of way for the north traffic, but the south traffic cannot be met with the best coordination. So this is the issue, how to set the offset. And so the simple idea is considering about the return travel time should be the multiple of the cycle time. So set some cycle time, then such a best coordination distance is determined by this one. With some given the travel speed, because of the travel speed is given by length divided by the speed. And so in our practice, always considering about this kind of the special case that the very well coordinated lengths or the worst coordination conditions with that changing the offset values, no delay reduction or no stopping conditions achieved. And to discuss demonstrating the control delay, okay, for this kind of the best conditions, then we can achieve the no stop delay situation for both directions, northbound and southbound. On the other hand, for the some intermediate situation of the length of this one or this one, then these situations no effect for the total delay or average delay for both directions. And also, we had a knowledge about the cycle length optimization conditions, cycle length settings for the coordinated signals also. And basically, the cycle length, if the cycle length comes to be longer, then the minimum achievable delay, which means the well-coordinated offset values, but still we should accept some level of the delays, then it will also monotonously increasing. And yes, okay, sorry. This achievement was done by Professor Koshi. Actually, the publication was 1989 in English, but he already proposed this concept in 1975 in Japanese. And so the Japanese manual applied his concept so that in Japanese practice also following this kind of idea. This also showing the sensitivity of the coordination settings. And so at the best situations of this link length, or from here to this link length, then we can achieve the highest the coordination effect, which means when you set the most appropriate offset value, then you can achieve the minimized delay. On the other hand, at this link length situation or this link length this situation, so then maybe you can have any arbitrary offset values to achieve the same delay levels. And but this knowledge is very limited because this is only introduced for 50% green split for two intersections which connected to the one link. So this is a very ideal situation consideration only. Only one isolated link with two intersections connected. Then we can apply this kind of idea. But the reality is maybe not 50%. Even those are same, or those two green space should not be the same. So what will happen? And several years ago, this is a joint studies, and we analyzed the characteristics of the signal coordinations. But I will skip on this topic, and also generalized the achievement we got very recently. Okay, and this is also something interesting things that with some the range of the cycle lengths, we can achieve the minimum or zero delays, and this is the characteristics when we have the different green split value. Okay, then come back to the practice in Japan. Okay, I have only six minutes right now. So what is the offset pattern selection method applied for Japanese traffic control center? So this is the example of selecting tables. So with the detector informations, so one direction inbound flow ratio and the outbound flow ratio, applying those values, And with these values, okay, if the value is located here, okay, some pattern of the so-called equity 2 should be applied. But if the rather low outbound flow ratio, but on the other hand, inbound flow demand level is high, then semi-prioritize to the inbound, or rather priority to inbound, or something like that. This kind of idea is introduced, then put the offset values. And in addition, this kind of offset selections are done for example, every 15 minutes, every 5 minutes, or something like that. And if the offset values are changed from the last 15 minutes to the next 15 minutes, then we should change the offset value. But the offset should not be immediately changed, because of the drastic change comes be the very short green split or very long time green time. So we had an idea also of the maximum change ratio. It is 12.5% of to the cycle length, and generally with the multiple cycles, and try to adjust the offset values. And also we should be careful that the changing direction, the offset value increase or decrease should be carefully selected, because the two adjacent intersections having the different direction of movement then comes to be the reverse offset conditions, which comes to be both sides facing with the red signal and come to be rather serious long queue lengths. Then, as I mentioned, that the kind of forming the subnet systems is based on the tree shape structure, not having the closed loop. Having a closed loop, then we cannot have the appropriate parameters for all the lengths, links. Sorry. And sometimes also we should reforming such kind of subnets. So the change shape of those subnets is also considered for every 15 minutes and so on. Maybe the time is very limited, so just explaining about several application cases published. First one is in 2013, the Tokyo Metropolitan Police Department experienced introduced. So from 2009 in Tokyo, the split is calculated very frequently, and the traffic demand is applied not only the just measurement, but a kind of a prediction is also already introduced, and the cycle length is calculated with the formula, and offset is also calculated using some simulations. So pattern selection is the rather the old fashions, and also the long the calculation duration required, but the rather short, and the rather theoretical form applied. Sorry, I don't remember what is this. Okay, this is the Tokyo Metropolitan application, Metropolitan Department practice started in 1995, as I mentioned, that pattern selections like using those tables. And okay, sorry. And the another things is sorry, when is this? The so-called moderato is a Japanese some parameter generation systems that they based on the very similar concept of the flow ratio, but the new idea is a load ratio, which could applicable for the oversaturated situation. It is something replaced the indicators with the flow ratio, and try to set the green split with this one, and set the cycle lengths. And the offset is not all calculated by the simulation based. Some pattern based pattern selection applied for oversaturated situation in the beginning, But at this moment, they applied any conditions. Okay, in 1999. And these days, kind of some progression of the arrivals are also considered and already applied. Okay, then that's all my presentation for today. Thank you very much.
Thank you, Professor Oguchi, for your informative presentation. So we are going to have questions from the audience. So if you have any question, please raise your hand or write your question in the chat of Zoom, or unmute your microphone and ask question directly. No questions from the floor?
Sorry, if I may.
Okay, so Daniel, please.
Yeah, sorry, thank you. Just a quick question. You said the police do the coordination of the traffic signals. So it's police is in the government doing it. There are traffic engineers within the police. Is that right?
Good question. Yes, a very few number of the traffic engineers are assigned to the traffic control. And on the other hand, especially in Tokyo Metropolitan Police Department, they have a rather large number of the traffic engineers inside. And another important thing is signal system industries, the companies are providing their knowledge on the systems, so that those company engineers are suggesting the appropriate system introductions and also parameter adjustment settings and the operations and so on. That's the Japanese practice.
Thank you.
I have a short question.
Yes, please.
Yes.
You showed us in one of your early slides, you showed us you replaced the ordinary loop detectors with probe, if I remember correctly. So is it practice or kind of still in the respect? Yes, this one. The replacement with probe. You are saying that you are going to use the probe data to replace roadside detectors?
Yes, maybe for today, I didn't have a time to talk about that, but as you may observe that yes, such a very large number of the intersections are connected with the traffic control center, and traffic control center, one traffic control center, for example, in Tokyo, is connected to the very huge number of the intersections. Yes. And those control are based on the detection information by the traffic detectors. Therefore, also they should maintain the very large number of the traffic detectors. But these days, because of the limitation of the human resources and also the monetary budget, they try to reduce the number of the maintaining the detector systems. Therefore, they are very interested in the introduction of using the probe information. So these a few years, they had a kind of a project, national project, and checking the usability of the probe information. But still, not it's a ongoing project. There are several projects, and so at this moment, not in the practice. That's the reality.
If I may, I would have also one question.
Hey,
Thank you, Oguchi Sensei, very much. Thank you very much for the very informative presentation. Some of your slides I still have to digest, I guess. But you mentioned in the beginning the progression speed, and you mentioned that it's around 30 kilometers per hour or a little higher, which in Germany would be unusually slow. So could you say something about the progression speed?
All right. 32 kilometers per hour was the first introduction in 1933. Yes. And at this moment in Japan, basically we apply the idea of such a progression speed align with the speed limitations. So in urbanized area, 40 kilometers per hour or 50 kilometers per hour is the normal speed limit in urbanized area. So we are basically along with such a speed limits.
Okay,
that's the reality.
Okay, since we have limited time, thank you, Professor Oguchi, for your presentation and answers. So if you have further questions, we are going to have the discussion session at the end of all presentations. So you can write your question in the chat so that we can go through after all the presentation. Thank you. So
Thank
the
you very
next
much.
presenter is Dr. Maria Salmons. You are here, right? Okay, so the floor is yours. So please
Yes,
start
I'm
your
in.
presentation.
Good. Can I start sharing? Share screen. I'm
Yes,
going
please.
to start my presentation. And you should see it now.
Yes, I can see your
Okay,
screen.
good. I'm going to talk about the coordination of signal control in the Netherlands. And the content of this presentation is the introduction to urban intersection control in the Netherlands, policies on intersection control in general, arterial coordination, because we're here for that, some of our methods used, the state of the art of intelligent traffic signals, bicycle coordination, and the blue wave. And I'll leave that to the end to see what that is. So this is the Netherlands. We have 17.5 million inhabitants. We have 8.7 million cars, and number of bicycles is 23 million, so more bicycles than inhabitants, and this is important also for coordination. We have only 6,000 traffic light controllers, a bit less than in Japan. And from them, 85% are vehicle actuated, so reacting on vehicles. 2% are traffic dependent. 13% are half-star or semi-fixed. On 0% fixed time and 10% intelligent vehicles. So this is what an intersection in the Netherlands looks like. So a lot of cyclists. And here are the loop detectors. We have a lot of loop detectors at the beginning and further downstream. We have also push buttons for pedestrians and cyclists. Cyclists have both push buttons and detectors. We have also cameras, radar, mobile apps, but far and the majority are detectors, loop detectors, everywhere in the Netherlands. Every intersection. And the cycle time and the clearance time are determined beforehand, of course, and it's very important to the 10th of seconds. So it depends on the when the clearance area here, when a car wants to enter the clearance area, and here's a car that has just left the clearance area. You calculate to the 10th of seconds how much time it will cost. And this is implication for coordination. In the morning, you have this conflict, and you will have a different clearance time than if you have in the evening traffic coming from this direction. So if you coordinate in the morning on this direction and in the evening on this direction, you have to keep into mind that you will have a different clearance time. So different program. The policies on coordination. Intersection control should be credible and understandable for all people using it. So people on the coordinated direction, they expect that the signal will not turn red when moving to the next intersection, that they don't have to stop for every intersection. But people from the crossing directions, they do not want to wait for nothing, because we have a lot of intersections that are vehicle controlled, so controlled on the appearance of vehicles at the intersection. So people are used to, I'm here, I do not see any traffic yet, I'm going to cross. So when you have coordination with a lot of waiting time for crossing traffic, people tend to run red. So intersection control should be credible and understandable. So avoid, when possible, unnecessary stops and waiting, both for the crossing directions and for the coordinated direction. So we have to balance between those two. We should avoid spillback. This is very important reason to apply coordination. So if you have an arterial with a lot of traffic, you might have spillback if you have unnecessary stops. So the downstream intersection might experience spillback, no, upstream one. The balance, you have to balance the priority for buses and coordination. So if you have buses and trucks that will have coordination either on the coordinated direction or on a side direction, you have to balance between those two. And you have to inform the traffic participants. If you have a certain intersection that's controlled by coordination, so there's downstream intersection that has traffic coming to the upstream, you have to inform that there is this intersection control. And there's several types for coordination. You have the hard coordination, coordination within one control program, on the intersection, when you have to move over two stop lines, or between the intersections. If you have two intersections close together, you can coordinate them within one control program. You can have greenways on arterials with platoon coordination for 3 or more, or you can have network control when you have intersections not on one arterial. And the major part of this talk is now about greenways on arterials. So we have halfstarre regelingen, called in Dutch. This is semi-fixed time control. You have a fixed cycle time with the offset and the control between the coordinated intersections. So you have coordination on the main directions, but flexible green. And I hope you paid attention to the last, the former speaker. He excellently explained what the fixed cycle time should look like. So I've added these formulas from the handbook on traffic control in the Netherlands. It depends on the load at the intersection, but also on the distance and the speed. So it depends on the demand here. 90% of the time the queue should be dispersed, and this is the distance between intersections if you have 3 intersections, and this is the speed. So it's half star, semi-fixed. We have green split based on the detector info. So you have to optimize the green wave further or limit the waiting time for crossing directions. Now, how does this do? The green time coordination is limited, and that is not a problem because you have complex platoons, so less dispersion. And how does this work? We have 3 intersections, and these are the phases. So first in this direction, and this is the coordinated direction. So in this direction and this direction. We have also detectors, so we can detect how well the coordination is. So if there's platoon dispersion, so that the platoon is close together here, but not in this direction. Suppose you have the platoon dispersion, you need more green time for this direction. And suppose in this particular situation, you measure by the detectors, there's no traffic on direction 9. Then you can say, well, first we have these phases. So first the east-west, then the turning, and then the north-south. South, we can say, well, for 9, there is no traffic. So we can say we need these phases, the left turn instead of this left turn. And we can prolong the green time of 2. And then we have optimum coordination and no problem for the crossing direction at intersection 3. As I said before, the speed is of importance, and you have to inform the people that there is a certain speed they can have the green wave. So we have Odessa. When you see a name abbreviation with a star, so here, this is the company, and this is the method. So the company consultancy DTV has Odessa, and this gives speed advice for the semi-fixed time control on 70-80 km/h roads. So not for 30 kilometers, for 70 or 80 km/h. You can have coordination up to 1 kilometer, and these signal givers for every 500 meters, and you should give a credible control. Therefore, it's only used for fixed time control. And this particular location, what did I do? Is for Bergen op Zoom. It has 9 intersections. So this for the credibility, this is only used for semi-fixed time control. I will show more methods, but they are not used with the signal, this type of signal giving, because you have to be certain you have the green wave. If people experience I'm keeping this speed of 65 km/h as indicated, and I do not have a green wave, I'm very frustrated and I won't keep the 65 km/h. On the other hand, you might have people that say, I've never experienced a green wave, and complain at the papers, and you write a letter, dear editor, I never experienced a green wave over there. You have next paper people saying, oh, but you're speeding, because if you stick to this certain speed, you will most certainly have a green wave. So people get used to correct information. There once was Utopia Spot in Italy, and we tried that in the Netherlands as well. It's a combination of coordination and bus prioritization. And we said, well, we haven't bus prioritization ourselves, so let's try it out. But it was not well balanced for the Dutch situation, so we left this method, because the bus priority appeared to be too disruptive if the bus came from the non-coordinated direction. In the Netherlands, we love conditional priority. So if a bus is late or on time, it will have priority. If it's early, it won't have priority. And we won't prioritize it every cycle. So we do not use Utopia Spot anymore. What do we use? The consultancy of Vialis uses TopTrack Flex. TopTrack has a central server, and it's based on Transit Online. It's a very well-known method from Great Britain. You can't find everything about it online, but one thing I will explain, it uses performing indices. So you can say beforehand, I want to determine how many stops and how important I think there should not be stops or delays on both the coordinated or the side direction. And then you can determine beforehand and say, I will have these objectives for these calculated beforehand, and you can check it beforehand. If I think these stops and delays are important, then you can determine beforehand whether it is suitable. Calculated. So not only for simulating beforehand is also important, but you can also calculate what will happen in these situations. So this one hand, the TopTrack part is for coordination with a green window fixed, but a flexible part determines what is the green time distribution, the green split at local intersections. This is vehicle dependent and with a certain objective function, so the maximum waiting time, for instance, for the coordinated direction. But the green wave is not really guaranteed. Not as a semi-fixed, you won't have a guaranteed green wave, but come very close to 100% green wave if you give a high weight to the coordinated directions. And here is an example, the Almere Veluwe Dreef, with 1, 2, 3, 4, 5, 6, 7 intersections, and they're very happy with it. Yet another consultancy, DINIC, has the Inflow Method. This is quite different from the VIAS because it has no central server and everything is done locally with local optimization by communicating by nearby intersections, and it's planning per minute. The optimization is based on weighing factors and priority, and optimization is bounded by maximum waiting times. Also have priority, with the emergency service can say, hey, I'm an emergency and I have a short distance radio, we communicate. Also public transport, but this is conditional when they are on time or late. But trucks can also request priority by an app, Greenflow Truckmeister app, combined with face information, so the truck gets time to red, time to green. This gives soft green waves. For large distances, it will lead to a variable cycle times, so it's hard to make a green wave, but again, with a higher wave of platoons, you can realize semi-green waves, but it's less good in making green waves than the top track. So here in Delft, I live in Delft, there's a new type of this intersection control, Inflow. It uses glass fiber connection, and you can see for the intersections which vehicles are coming, and you can predict the intersection demand and give try to make a green wave. This is very new, just last year it was installed. And also they are very happy with it. So we have also intelligent traffic control. This is now new in the Netherlands. It is installed as we speak. 700 at the start of January, 700 intersections with intelligent traffic control, in Dutch called IVRI. So ITLC, the Intelligent Traffic Light Controller. It can use common intersections, and for more advanced vehicles, they can communicate with a roadside facility. But the new fact is that everything is now stored in the cloud, whether it comes from detectors or whether it comes from more advanced vehicles. Everything is stored in the cloud, and we can say we have a priority broker. It says, well, I see now a platoon coming. I will give priority to this platoon. So you can also control in the cloud. Before, with the normal VRI's, so normal traffic light controllers, where the problem that if you have controllers for different manufacturers, they can't communicate. And nowadays, where everything is in the cloud, you can communicate. So if you have intersections from various manufacturers, it's more easy to communicate, but it makes network control, so also coordination, easier. So we're very happy to have this IVRI's. And the idea from intelligent traffic control is to prioritize, inform, and optimize. So we have more effective data communication. We have, although it's a small percentage, vehicle to roadside, infrastructure communication. It's now 5 to 7% of the vehicles have this possibility. And we can give time to red and time to green or speed advice. Well, we can have in-car information. You see over here, in-car 70 kilometers per hour. Or you can say, well, this is the time green that remains. When you give in-car information, the credibility is of importance. When you give information, you should give the same information to all cars, because you can't have one car do the one thing, so keep 70 kilometers per hour, while the car in front gets the 50 kilometers per hour information, and it will brake, and you have the probability. And so you should give the same information to all cars. So it's basically the same as Odessa, giving information at the side, roadside, because you have to give all the same information. And is also the drawback, you have more fixed time. If you have a fixed time green, then the credibility will be very high. So we are a bit afraid in the Netherlands that car manufacturers say, hey, I want to give in-car information, and it should 100% be credible. So now we have all nice detectors and flexible green times, and then you have to give 100% credibility, and this is not possible. So we are very afraid for more fixed time green. And we have coordination for bicycles as well. As I said, we have a lot of cyclists, so we have bicycle coordination. We have arterial coordination based on average speed of 15 kilometers per hour. Here's an example. In Almere, in Cinema Dreef, in two directions, you have two intersections. When you leave the stop line, at one intersection, you will certainly have green. If you drive at 15 kilometers per hour, you're certain at the next intersection you will have green. But we have a large speed differences for cyclists. One cyclist drives, has a normal bicycle, is a bit slow, so 12 kilometers per hour. The other one has an electric bicycle. They're also in the upswing in the Netherlands, and drive 22, 25 kilometers per hour. So a large difference in speed. So you like to give speed advice to cyclists, most certainly if you have coordination, but also for isolated intersections. Cyclists hate to stop and to start again. So at intersections, at local intersections, we give speed advice. So here is at the Erasmus Bridge at Rotterdam, they give 3 seconds more green. This is at a bridge, so this is at the foot of the bridge, so you have the slope of the bridge, which is a bit steep. So you have a higher speed, and then you see in a distance, 3 seconds left. What shall I do? Shall I continue my high speed, or shall I apply my brake? So you can also have the speed advice for the cyclist, and you don't have to determine yourself. There are two apps, even more coming up. I'm now explaining two, Ring Ring and Schwung. Ring Ring informs the cyclist 100 meter upstream. So I'm going to, I've seen you, then you hear one ring from your mobile phone in your pocket. When the light turns green, it will have, it will say, well, I'm going to inform you that the green time will be shown soon. So if you want to accelerate, do it now, because in a few seconds it will turn green. Schwung learns from the cyclist behavior. If you have coordination on a certain direction, but Schwung learns you're not going to make use of this coordination because you're going to leave the arterial, then the green time will not start earlier. So you know exactly which, if there are cyclists that want to use the coordinated green, and if there are no cyclists, you can determine this green split will not prioritize the cyclists. So this is very important. It won't give green if not needed. This will, of course, enhance the credibility. The last slide is about coordination on waterways, because we have not only coordination on the road, but also coordination on our waterways. And you have a bridge opening, over here. And the ships know the opening times of the first bridge. And if you have this opening time, then you will be certain that the next one will open when you sail at a certain speed, and the last one as well. So we have also the road traffic, and they have to wait, but we can communicate this as well. So if you have come here, you know beforehand, I should stick to a certain speed because I can drive slowly because we have to stop here, or I can still continue because the bridge will not be opened. So these bridge openings are also communicated to road traffic. This was my presentation. Are there any questions? No.
Thank you for your presentation. So again, if you have questions, please raise your hand or unmute and ask her directly, or either you can also write your questions in the chat.
Daniel, Suta here again. Oh, sorry.
Oh, okay, so please.
Yeah, just a quick one. With the sharing of information to the public in terms of upcoming green time and cars and stuff like that, is this going to kill all the adaptive work that we're doing to make traffic signals smarter? And given how far advanced you guys are in terms of having vehicle-to-vehicle and vehicle infrastructure out there, 5 to 7% of the cars, where are you guys sitting with this concept of fixed time killing adaptive?
Yeah, we are really afraid of that. On the other hand, we are also doing research on it that we can try to predict the green time as well as possible. So there's ongoing research at the moment because we hope, so most certainly hope we can still use that all adaptive control with a correct time to red and time to green. Also, when you give this information to increase the credibility, you also have to say at what time you are going to convey this message to the public. If you are not 90% sure, you are not going to give this information. But if people expect this information, you might end up with complaints. I want to see this information. So then you have to inform the public. We only give this information when we are 100% sure. So maybe you have seen the picture of the green time displayed at the Erasmusbrug. This is only given. You don't see any information when it's not certain because there's so much traffic and we're not going to end the crossing direction soon, and we don't know yet the green time, maximum green time is not reached. So we're not going to convey this information. If you know there's no more traffic left, then it will take some seconds, and then you will show this information. So this is the way to go, I think. But we won't leave our detectors. We love our detectors. There are detectors everywhere in the Netherlands. One of the traffic engineers said, when the world is going down, the Netherlands will stay because we're tied together with all the detectors. So we won't leave it.
But is there any problem or issue of the cost for maintaining detectors?
Yes, yeah. There's a really cost. You have to maintain them very well, and because we get now more and more info at the cloud, we can also have all kind of assessing dashboards that we can see all our detectors are functioning well. But also we have to have the money to repair them when they are broken. So it's cost, but we all think it's cost effective because the flow of the traffic is better and safety is better.
Can you maybe expand a little bit on public transport? As far as I understood, you have conditional public transport based on punctuality of vehicles. But in Germany, for instance, public transport is always very important topic as the backbone of the transport system. How is it in the Netherlands?
Before Corona or during Corona?
Well, before and hopefully after Corona.
Yeah, because now it's less used, but it's very important here in the Netherlands as well. But yeah, the bicycle is also very important. So it depends on which city you are. In Rotterdam, the public transport is far more important. And cycle use is less. In Amsterdam, both are very important. Well, it's also very, very important, but it's also a clash sometimes between cyclists and the public transport. The students have a free pass to use the public transport either through the week or in the weekend, and they make much use of it. But people state, oh, those lazy students, they should all use their bike. But on the other hand, the bicycle lanes are so busy with cyclists as it is. So maybe it's good that they also use the public transport. So, but when the conditional priority is, of course, very important, why should you give priority to a bus that is early? Then you have to wait at the bus stop. So I think conditional priority is important. And this is communicated. I'm bus, that and that. I'm early. So the signal knows you're not going to have this priority.
I was asking in regards of coordination, because that usually makes it very difficult to predict the green time if you have those advisories. So it makes it even more complicated.
Exactly. Yeah. We totally agree. This is the question that always pops up when you say we're researching time to red, time to green predictions. Oh, what do you do with buses? Yes. But when you have more information, they're coming more upstream information, because we can now handle everything in the cloud. You know where the bus is, you know when it leaves the bus stop, and you can predict what the speed will be. So it will become somewhat easier.
Well, if you know when the bus leaves the bus stop, but that's just an assumption. So
yeah, no, you know when it leaves the bus stop. If it communicates that I'm now leaving the bus stop, and then you have a model what the speed will be. You have a certain demand on this arterial, and then you can predict the speed of the bus coming to the next intersection. It will see. But of course, it also depends on the distance between the bus stop and the intersection. Is well upstream, then you have time to do this prediction. If it's near the intersection, you have to say, well, it most probably will in certain seconds, and it will be more disruptive.
Okay, exactly.
Okay.
Can I have a short question as well?
Yes, please.
Yes, thank you very much for your interesting presentation. We can always see many new things in the Netherlands. In addition to green wave, you also have blue wave in the waterway. It's very interesting. Yeah. I have one question regarding how the decision is made. I mean, when and where to implement the signal coordination. You mentioned that over 80% of the intersections are operated in a vehicle-accurated mode. So how is this necessity to implement signal coordination comes up? Under what conditions you decide, for example, this arterial or this highway should be coordinated? So what is the procedure for that?
Yes, it's the policy. If you say, well, we have a very large amount of traffic on a certain direction, and we have a certain policy that we should keep an eye on the environment. So we have multiple stops here. Rather try to coordinate this direction. And some of the traffic engineers hold the opinion we should use more signal coordination here in the Netherlands. So it depends on your policy, but we're very used to isolated intersection control.
Yeah, so it can work quite well in the low or medium traffic load case. So
you can have also soft green waves. When you have multiple detectors, then you can see a platoon coming. And when a platoon is coming and it's measured on the detectors, and then you can extend green at vehicle activated control, and then we have a semi-green wave. So there's also a reason not always the method of the intersection control is used. But as I shown you the Delft situation, the inflow with a glass fiber connection, this was new. This was beforehand isolated intersection control. Yeah. Now it's inflow granting more green waves, but not real green waves because they are not very well guaranteed. But if you have high weights, it will guarantee semi-green waves. So more often green waves than for isolated intersection control.
Okay, thank you.
Okay, if there's no more questions, we'd like to move to the next presenter. So thank you for Maria.
Yes, I like to do that.
The next presenter is Mr. Daniel Suter. He is going to introduce the case in Australia. So please start your presentation.
Thank you very much. Can you see my screen?
Yes.
Beautiful. Thank you, everyone. All right. So to give you a bit of information from the Australian side of things, practices. So myself, I'm working for a company called Transmax. We're a government-owned organisation, but private government-owned. We work with a lot of the road authorities across Australia, and I'm here talking not necessarily as a Transmax employee, but as a traffic engineer in general. I'm a friend of Ashish Bhaskar from QUT, Queensland University of Technology, and so I'm here. Basically, he's invited me to come and have a chat because we work together quite a bit, and I've worked across a few road authorities across Australia, so I've got a fair idea of what most of them do. By no means is what I'm going to present meant to be the be-all and end-all, and I'm not saying this is how everything is done. It's just merely what I've come across in my 18+ years of doing this, and I think it's a pretty fair representation, but I'm not going to pretend that it's everything that happens in Australia. So to jump into it. So some context. Within Australia, we've got 3 levels of government: federal, state and local councils. Federally, not much happens in the signal coordination space. They don't really get involved at all in that. They're more responsible for funding sources, big projects and things like that. They don't really get involved. It's at this state level that the majority of our signal coordination work is done. Some states have local councils operate their own traffic signals and do their own coordination, their own traffic management centres, but predominantly it's at the state level that coordination is done, and it helps simplify issues such as who has priority in terms of this or this type of road. The council road's more important than the state road. No, by letting one organisation manage the lot, it all just comes down to looking after the general community. So that works very well. We've got a whole series of different types of road layouts and types of roads, everything from city, CBD styles to urban to rural. So, and everything in between. We've got a population of 25.5 million people in Australia and around 14,000 traffic signals roughly around Australia. So just to give some context. And we've also only got 2 traffic signal systems. So we've got SCATs and Streams Arterials. Streams itself is an ITS platform, of which one component of that is the arterial control, and SCATs. SCATs is by far the most widely used system in Australia, but we're very lucky that we've only actually got 2 traffic signal systems. It makes it a lot easier to work across jurisdictions and share skills, knowledges and resources. Across the top of all this, we've got some research knowledge transfer organisations. We've got the Australian Road Research Board, and we also have the Australian Road Research Board and AustRoads, which are funded through all the different road agencies across Australia, and they come together to help share knowledge and produce standard guides and alike. So we have Australian standards across for governing the majority of aspects to do with traffic signals, which is both really good and a little bit restrictive on what we can do, but it is well regulated. So jumping on. So some naming conventions, just to make sure we're all talking the same language here. So we talk in phases, A phase, B phase, C phase. So we're phase-based or stage-based control, not movement-based. There's a little asterisk there because through the personalities that we write, which controls and says this traffic signal is this traffic signal, we can do quite a lot of tricky stuff with that, which we can mimic movement-based like controllers. We talk about phase splits, cycle time and offsets, which is very common to what we've heard today. Down the bottom are the various parts of the traffic signal. The various parts of the traffic signal, and it's the rest period for the vehicle group, which is where the traffic control systems come into play. Likewise, the clearance time, which is the flash and don't walk in Australia, we can reduce that time if there's no more pedestrians detected. So, moving on. Oh, sorry, some of the typical times and things like that we've also got. So typically across Australia, we've got our cycle lengths range from around about 50 seconds right up to 200 seconds. So we unfortunately have some very, very large cycle lengths. It's the nature of our roadways. We do have multi-lane. It's not uncommon to have 3 lanes on the through and a double right on each approach. We do get some very large intersections, but we also do get large cycle times through, in my opinion, poor practice. Our speed limits, we work between 30 kilometres an hour up to 100 Ks. So we do have in the Northern Territory traffic signals on 100 K roads, but generally we try not to go above 80 kilometres per hour roads to have traffic signals on them. Okay, so some on the hardware side of things, our traffic signal controllers are all of the same spec. So they all have to conform to an Australian standard 2144. And that means that we're in an isolated little bubble with our traffic signal controllers. They work extremely well. They've been really good to us, extremely reliable. But some of the stuff that we're hearing from Netherlands and the like, we haven't gotten as far as we'd like to in some of those aspects because we are both protected and restricted by the Australian standards. For our lantern configurations, we use multi-core cable from the traffic signal controller. So each signal group or movement will be on its own electrical run, with the traffic signal controller essentially doing the switching of the signal groups and the monitoring fault reporting. For a lot of our intersections, or most intersections across Australia, there's a modem or a field processor located within inside the traffic signal controller, which has some smarts on it, as well as enabling the communications back through the ITS network to the streams application, to the server, to the workstation. So in each road authority, they'll have their own setup, very similar across Australia, but they are their own systems across Australia. So there isn't one system across Australia. Each state has its own system, even though we're using the same software for the majority of us. Also, we do have detection on each lane. It's pretty much everywhere we go, we do have a detector in each lane. We definitely don't have the same extent as the Netherlands, but we do have detectors on each lane. The maintenance of them varies as you go around state to state, but generally they're pretty good. Side streets are definitely maintained. The detectors on the side streets, so in the diagram here, detectors 6 and 7, which will place a call for the right turn coming out, they've monitored and maintained. So in Australia's context, we're very safety conscious. Almost too much, but if they were to fail, we see it as a car pulling up. They won't be registered by the traffic signal controller, and therefore they won't be given a green. The motorist may take into their own hands to proceed across the stop line without a green signal, and we see that as a pretty serious safety risk. So it's generally well maintained for the traffic signals. And to go further down that path, the two diagrams on the bottom here are from Austroads, which is one of those organizations that creates publishing guides. And the two diagrams show what sort of a lantern arrangement you could have at a set of signals. Our Australian standards say that we only need 3 lanterns per an approach. But as you can see here, we've got 6 through movement lanterns lighting it up sort of like a Christmas tree on an approach. So we are very conservative when it comes to safety, and safety drives most design and policy decisions for us. So it's good and bad, but that's the Australia we live in. Okay, so in terms of coordination, majority of our traffic signals are semi-responsive. So in the SCATS land, so both SCATS and streams were developed starting in the 60s, 70s, funnily enough, just around the same time. So nowhere near as early as Japan, but then again, we haven't quite hit the 200,000 mark for traffic signals either. So we started developing in the 60s, 70s. Streams was originally put in on the Gold Coast, where a series of roadways down the road, there was a long line of cars going to the beach, and they needed traffic signals to coordinate the traffic and allow cars to come from the side streets and pedestrians across the road. So in 1969, they put in the first coordinated system for streams. And SCATS, it was on its way to development, but they say it started in 1975, but I think the origins were probably about 5, 6, 7 years before that. But 1975 is the official, and they said SCATS came along. So in terms of how SCATS operates, it works with equisaturation on each approach. So SCATS essentially works by looking at the degree of saturation on each approach, by measuring the current flow versus the best flow on that approach, and trying to optimize so that each approach has a degree of saturation of 90%. This is using the incremental split plan selection 35 within SCATS land, and it works extremely well. The feedback loop at the intersection works very well. So it has variable splits and cycle time. It does that, continually adapting its cycle time and splits. And the offset is semi-variable. It has a low and high cycle length offset. And as per the academic documentation shown in the previous 2 presentations, just incrementally going with your offsets from 10, 11, 12, incrementally from 10 to 20 isn't really a good thing, because you do land in that area of the offset not being optimal for the cycle length. So that's probably about the only downfall of SCATS. It doesn't do, in my opinion, the offsets well at all, but it works very well. It's used across a lot of Australia. It has a very powerful if statement inside SCATS, so you can do a test and if this, do that for a lot of different conditions. You can test at the intersection down the road if it's in B phase, do an early release of the phase you're currently in at this intersection. So it's got a very powerful if statement, and it has a schedule manager a scheduler to manage a wide range of situations. So for a lot of installations in the very congested areas, they'll actually run a scheduler to lock in the cycle length and lock in a split plan or a link plan meaning the offsets along the particular direction, so that the intersections operate that manner for that known condition. So they know that in the very busy part of the morning peak, we want to give bias to the inbound direction, regardless of what weird detection issues may be occurring at the individual intersections. We know this is a plan that we want to override. Then as we go towards the end of the peak, let SCATS continue to do its own optimization. On the other side, Streams uses, it has user-created plans with the ability for unused time for each phase to be transferred around. Personally, I don't think it's probably as optimal as SCATS, but it does have its benefits in terms of the selection of the plans, the creation of the plans for the offset. For a particular route, coordinated route, we can select the optimal offsets at different cycle lengths, where an 80-second cycle length works really well, but a 90 or 100-second cycle length is poor. But then again, at 110, it's a good offset for bidirectional coordination. We have that power. So we can do time of day plan selection, which is very similar to the Japan semi-actuator, I think it was. Apologize if I got that wrong. But where we follow a typical day, and we can say that at this time of day, this plan should be running with these offsets, these splits for cycle length. And we've also got dynamic plan selection, where looking at a corridor, it can look at the occupancy of the through movements along that corridor and say, we're operating at a high occupancy with a bias towards the inbound direction, and that will select the inbound high direction plan and apply that one. So Streams also has a very powerful if statement with a little asterisk there. Because it's an ITS platform, it can bring in inputs from more than just the traffic signals. It can bring in inputs from a lot of different areas, such as Bluetooth detector readers for travel time, water level sensors if there happens to be a flooded road. A multitude of different sensors can be brought into that if statement. So not only can it do the if statements at the traffic signal level, it is aware of the wider network as well, so which can be very handy at times. And it again has a scheduler to deal with a wide range of situations. All right. So our timing process, so road authorities now are focusing more on optimization. They're finally starting to get the story that the diagram there, which was in our Infrastructure Australia Report 2016 and sourced from, they referenced another source, and I guess I'm referencing another source as well. The benefit to cost ratio, if we do our traffic signal phasing re-optimization, we can get a BCR of 62 to 1, according to this report, whereas traditional road capacity building, i.e. building new roads, has a BCR of 2.7 to 1. The reason for that basically is it doesn't cost as much to re-optimize traffic signal phasing, because the majority of it's there, it's people's time. Whereas building a new road, that's going to cost a lot of money. However, you will never get the benefits that a new road will through the optimization process. The benefit to cost ratio is a lot more generous. So a lot of road authorities are finally coming around to that. I'd say we've been pretty advanced at that compared to some places around Australia, but we're getting more of a focus on optimization now, which is great. The prioritization process for which routes should we spend our limited resources on varies from public concerns to systematic processes. So some organizations, road authorities, structured process with multi-criteria weighted analysis to rank all their corridors and go, yep, these are our most important corridors, perform them the worst, let's go review them now. Whereas some organizations are still working on what I call the squeaky wheel problem, where whoever complains the most, that's where the resources are deployed to go look at that corridor. Likewise, the coordination philosophies that are used out there, they vary from a very mature movement and place style. I'll talk a little bit more about in 2 seconds. Again, back to that squeaky wheel of, hey, I'm complaining about coming out of this side street. I've talked to the member of parliament, the member of public, I've gone to the councillor and whatever it is, so I want my journey to work to be better. So we range between those two. In terms of maturity, the Department of Transport and Main Roads in Queensland has a network optimization framework now, where as part of any infrastructure works that they do to upgrade a road or whatever it is, they basically ask the department to go back and say, have you actually re-optimized the timing plans? Have you made sure we're getting the most of that corridor before we go and spend a lot of money to get benefit? Likewise, they have options in there for minor works, where it may be do a pinch point analysis, and where there's a pinch point in your corridor, an extra lane widening might be needed before we build a massive overpass or a bus priority jump or whatever it is. They give a whole heap of different options to be explored before you come asking for the large dollar projects. So that's really good that's been embedded. Over in Western Australia, they've got a concept of route manager. where they have traffic engineering roles, where the traffic engineer is put through a rotation program to learn all facets of the business, and then they're responsible for the operations of an entire route or corridor. And the benefit of putting them through that process is, instead of having just traffic signal engineers who play with traffic signals and know traffic signals only, looking at a corridor, because they've been taught across a breadth of different knowledge areas, they'll look at the problem holistically. So they'll look at it and go, well, the actual issue here isn't the optimization of the signals, it's a parking on the approach to the signals, or it's actually 3 signals down, we need to ban a right turn to allow the traffic to flow better, and doing a holistic look, but in a structured way. I know myself as a traffic engineer, I try to work that way, and over time I'm getting better and better. But when I first started playing with traffic signals, I didn't know anywhere near as much as I do now, and I did look at the network from a traffic signals perspective only. So the route manager approach is a really good way to go. Likewise, in Victoria, the Department of Transport Victoria has a movement in place methodology, where what they've done is they've looked at the entire road network across Victoria, and they've looked at each individual corridor, and by time of day, and they said at this time of day, this corridor is a heavy freight movement, has highest priority. Second priority is general public. This corridor over here, or this section of this corridor, it's actually a place. It's a shopping strip mall. So pedestrians and cyclists, active transport has priority, and second priority is general traffic. Third priority is public transport. Fourth priority is heavy vehicles. And they've defined that by time of day for each part of their corridor across the entire network, and they've embedded that into their processes. So that means that if a new development comes along, it has to align to what's been predetermined, the priority of that area. So if a new development comes along and they want to expand the roadway to multiple lanes, that's going to reduce the level of service for pedestrians. And if the pedestrians have the right of way there, it won't get up. They have to change their development. Likewise, if a member of the public complains about the lack of progression along the road, and they look at the plan, it says, sorry, public transport has priority here, they've got something to stand behind and say, no, we're giving priority at this time of day to this class of movement, and that's that. So a very mature and defendable, logical way of dealing with managing the road network. But when it comes to actually doing our timing process, we've got 2 methodologies that I believe it generally falls into: first principles and modeling. So first principles, it's a limited data review. It's more going out on the road, driving the corridor and getting an understanding. And this is my bread and butter. This is what I've spent the majority of my career doing. Using things like tools like space-time diagram, volumes analysis, but they're more to give you an idea of how the corridor is operating, and you're spending more time living and breathing the corridors, driving along the corridors. Cycling derived from space-time diagrams and your observations on site for that particular traffic pattern. The splits and offsets, again, you do use a bit of data, but a lot of it is the plans being developed and refined on site. On the other side, we have a modeling aspect, a modeling approach, where we do a full configuration and data audit, because if the data inside the system isn't accurate, when you're extracting data later, or the system is using that data, it won't be working as efficiently. We do a review of that data as well, still driving the corridor to get to know it, and then we'll use modeling packages to produce calibrated models. Using those, we'll get optimal plans out of them via model output, and then we'll go out and put them on street, testing and tweaking the plans on street. And we'll also do a data collection exercise to verify the results, to make sure all the effort that's gone in was worthwhile. The modeling approach, having looked after a group inside one of the authorities doing it, it's very data intensive, very time consuming. It is, if you don't make a quality calibrated model, garbage in, garbage out, but you do get the best results, finding that absolute optimal outcome. Whereas the first principles, it can be a very quick to produce results, and it really does follow that 80-20 rule, but you need to know what you're doing. These days, we do a bit of a hybrid between the two, but they're the two normal approaches that are done. And to walk you through an example of doing one of these reviews of the corridor. First, we did the data audit, and essentially here, we just want to make sure that what is on the road is reflected in the traffic signal system to make sure that, yes, lane 1 is lane 1, lane 2 is lane 2, and aspects like that, just to make sure everything is matched up. We then do a data review. Whoops, apologies. We then do a data review where we're looking at the volume profiles, occupancy profiles through the various approaches and movements, and we're doing some checking to make sure the flow of vehicles leaving one intersection is arriving at the next intersection, or if there is a traffic sink or source between the two traffic signals, just making sure that the data matches up and it makes sense. We're also looking for undercounting, overcounting. Whilst we do have a lot of algorithms out there watching the detectors to make sure to observe them when they fail, there are also issues where double counting may occur that we've got to make sure we're aware of that before we get too detailed. We then look at our intersection groupings to make sure that we are coordinating the traffic signals that we do want to coordinate, that we do get benefits of, forming discrete groups of traffic signals that we're saying these intersections we do want to be coordinated, not strictly through all different traffic patterns, but these are the ones that we want to do coordinate, and we do have natural breaks. So I guess because we haven't reached the 200,000 mark with our sets of traffic signals, that's really blown me away. That there's 200,000 signals in Japan, over 200,000. But yeah, because we still have gaps between our roadways, we do have boundaries between us, where they're natural boundaries between our traffic signals. And we review the intersection grouping. We use cluster analysis. So that's pumping a whole heap of data through a generic algorithm, looking at clusters to identify the traffic patterns. We're finding that very useful to identify the various traffic patterns throughout the day. So we know that there's a morning peak, afternoon peak, a school peak, whatever it may be for that particular grouping of intersections. We use that to help give us guidance. Just a question's come up. I might jump to that at the end if that's okay, Maria. I will come back to that. Yeah, sorry, the cluster analysis, we use that to go through identifying the various traffic patterns. So we know that when we're creating our new traffic signal timing plans, that we're doing it for that right condition. And if the traffic patterns generally stay the same from 10 a.m. to 2 p.m., there isn't a lunchtime rush, then we know we don't have to go out every hour of that day. We can just go out and look at it once for that whole traffic pattern period. All right. Then the actual creation of the plan, we've got a lot of tools in both traffic signal systems. This one comes from Streams, space-time diagram, where we're able to adjust the cycle lengths, we're able to adjust the phase splits that we're allocating, remembering that some of the unused time can be rearranged. And we're also doing things like the phasing order. So down the bottom here, we do have a lot of phases. Again, that safety, we're very safety conscious. In Queensland, they're trying to ban all filter turns. There's a policy of filter turns are to be removed unless you can show why it shouldn't be, as opposed to the opposite of they can be used unless you show why it's dangerous. So we're taking a very safety approach. We have pedestrian protection inside Queensland. Sorry, filter turns is where the arrow drops off. So you're allowed to proceed across, do a right turn or a left turn, depending on which country, which side of the road you drive on. Driving on the left-hand side of the road, I can do a right-hand turn across oncoming traffic with the controlling green, red, yellow arrow dropping off to blank. And so you can turn across when it's safe to do so. So we play around with our phasing order as well and the offsets. That's it. So yeah, so we go ahead and play with a phasing order to see if a leading right turn would be better than a lagging right turn. And we also play around with the cycle lengths to see if we can get bidirectional progression, or if it is a northbound high plan, i.e. we're giving priority to the northbound, then the plan will be created as such. We also cater for various special features. So things like off-ramps, we want to make sure, off-ramps are the motorways, we want to make sure that the queuing traffic doesn't spill back onto the motorway. So that has to be taken into account. If there's bus priority along the corridor, school entries and exits, where we have for a very short period a lot of traffic around schools, because in Australia everyone drives their kids to school. The days of walking to school are long gone, it feels like. But yep, that's when schools are open, I should say, and shopping malls and things like that. So we've got to take into account when creating our plans all those various aspects. And then towards the end of it, we test and adjust on site. So we'll drive the corridor, we'll go out and drive it. We'll be on our laptops observing the data inside it. And we'll also be watching it through our CCTV systems. So we watch it from back at the office, reviewing the operations of the corridor. Preferably, we will go out driving it to make sure that it's operating as we intended. We're also looking at the benefits of it. So we use Bluetooth readers now quite a lot throughout Australia to measure travel time between 2 points, and that's processed by a system called Insight across pretty much most of Australia now. And from that, we'll also create reports to show the benefit to the community. The idea being that delay equals a loss of gross domestic product. So the way we see it, that there's a program out there called Sidra, a modelling package, and in it, it values roughly around 32 Aussie dollars, one person's 1 hour of delay. So using that as a sort of goalpost or as a measuring stick, we use that to calculate the travel time savings and the delay savings through doing the optimization process. And it works pretty well. It helps continue the funding for the important work of optimizing the network. And finally, the report will have recommendations. So we've done all this work, but we've observed that we need to make changes to line marking. We need to change the personality. We need some minor works done here to extend the turn pocket or whatever it is, and that will be fed back into the road agency. And finally, special considerations. So some of the things that we've got inside the Australian context, we do have some complex intersections. So this is an aerial view in Melbourne on the right-hand side here. There's multiple tram lines coming through it. There's cycle lanes, and it's basically a signalised roundabout with a whole heap of interaction happening around it. It is pretty okay. It's pretty easy to drive through it as a motorist because most approaches are one way with a lot of traffic signals showing you the way through. So it does work fairly well, but it is overall quite complex. Victoria has some very complicated traffic signals because they've got the largest, I think, tram network in the world, I believe, the most track in the world. And a lot of it is in lane as well. I think something like 70% of the tram network in Victoria is in the running lane. Likewise, in the bottom left here, this is on the Gold Coast, Queensland Gold Coast. The tram system on the Gold Coast has absolute priority. So through the traffic signals, inputs are fed into the traffic signal where it says, I'm coming, you will give me priority. So they give it absolute priority, and the way they've managed that is when they did the original timetable, they assumed they would have absolute priority and they must maintain that absolute priority to meet their timetable. So they go through some very complicated intersections. This one has bus lanes as well as a tram going through a major intersection. Those crossings there for the pedestrians are very, very long. We're probably looking at about 40-meter crossing. So the phase lengths here are very long, and that's where we get our high cycle times. So there's some interesting things there. And we also have smart Ped Crossings where we use radars to detect pedestrians. The idea being that we can shorten the crossing if there's no pedestrians on there and give the time back to the vehicular traffic. If there's still pedestrians there, it stays there and they can stay there up to a predetermined amount. Obviously, they should still continue the crossing, but we'll detect them as they go across, and they're getting rolled out more and more. Finally, just another special consideration aspect of what we manage. The movie world, Hollywood on the Gold Coast, they call it. We're on the Gold Coast in Queensland here. Movie world is a large attractor it's a very large attractor of a lot of people go there. They have events on at night time. And here on the motorway with the black lines, that's the motorway, 4 lanes each way, so an 8-lane motorway. There's a lot of off-ramp traffic coming from there to go to the urban environment around it. We have the general background traffic coming through from the suburbs and alike, and all that has to compete whilst trying to maintain, all the general background traffic of an afternoon peak occurs whilst there's an event and a whole lot of extra traffic wants to get to the event happening at Movie World. So we use something called decision trees through streams to manage those complex situations, so that we'll go through and using the decision trees to look at all the variable inputs, and if this particular conditions are met, do this option. If these conditions are met, do this option alike. And we can manage very complicated situations of competing demands using the tools that are available to us. So that was just final comments from myself, if I may. To me, in my perspective, more focus is needed on signal optimization. The number of people who optimize traffic signals across Australia is very limited, in my opinion. I'm not trying to criticize the road authorities, but in my personal opinion, I do think we need to spend more time optimizing the traffic signals, because I think it would give a very large community benefit. I think into our traffic signal systems, greater network awareness is needed. It's fantastic that we get detector information and stuff like that. But there's stuff like vehicle to infrastructure, getting more of that information, Bluetooth travel time, Google travel time, whatever inputs we can into our system so that we can make better informed decisions. One of the things stopping us in an Australian context is the traffic signal controller. The limit inputs that can come through it, but through ITS platforms, we can get around that and we can do more with it. Plus, I'd love to see an API style control for the traffic signals so that we can have other people developing algorithms and not just relying on a few companies to do it. So that's my 2 cents. Thank you.
Thank you for your presentation, Daniel. So we have a question in the chat. First from Maria. So, Maria, can you?
I thought I am going to ask this question after, but I clicked on my return button and make your go out of your concentration while I answered my question.
You're more than fine, yeah. Yes, we definitely do have a lot of dashboards. We've got a lot of information that's available to us through streams and scats. And there's a hell of a lot of information, almost too much information. It's trying to turn that information into intelligence is the trick. But no, we can see exactly what's happening on street through the systems, real-time detection, signal groups, pedestrian crossings, everything. My background as a traffic engineer working for road authorities, I prefer to get out in the car and drive it because there's a lot more that I'll see from the roadway that I won't see even from camera or the systems. So one of the limitations for the traffic systems that we've got in Australia is we don't know how big the queue length is. So we can have, 500 meters, 800, 900 meters between our traffic signals. We've got detectors located near the intersection or 35 meters from the stop bar, or in Scats land, 4.5 meters back from the stop bar. But I don't know if the queue is 500 meters or 5,000 meters. And that's one of the limitations that we have. I can do a lot of calibration and customization on those individual signals to make allowances for what's happening there. But I don't have a clear view of what's happening because we don't have a small grid network. We've got a lot of side streets that can feed in traffic that it's just not accounted for. We just don't measure all the traffic on our road network. So we don't have an accurate queue estimation. Even when we look at the modeling, even when we do, general traffic theory of queue lengths, we don't know the arrival rate. We know the discharge rate, but we just don't know the arrival rate. So.
Yes, we have also a Q estimator model, but you always estimate and not knowing what is happening in reality. And trying to add some more detectors helps, because when a vehicle is moved over one detector, most probably it moves over another detector, then it won't be gone until it reaches the stop line. But yet again, only if you have radar installed, you are most have a good idea about the queue length. Yeah. Thank you for your answer.
Thank you for your question.
Thank you. So let's go through the questions in the chat also. Another question is from J.R. Yao. Is square key wheel optimization online is actual application? This is his question.
I think that might have been more of a comment, and thank you for looking at that. I didn't realize the squeaky wheel optimization is an actual application. In the Australian context, there's quite a lot of, I'd like to think of people who have finished their jobs, retired, and have nothing better to do than to write into the road authority and say why the traffic is performing poorly. So we do have a lot of squeaky wheel, but I didn't realize it was an actual application. So that's great to know. Thank you. And to the next question, the personality. Personalities are the basic building blocks that says that this intersection is a four-way intersection with movements on each approach, signal groups, number of detectors and alike, and how it operates at the intersection. So signal group 1 and 2 can go green together, 3 and 4 go this way, right turns and all that. It's the code that determines all that to say that this series of lanterns and cables actually matches this traffic signal. It's where things like the all red time, the yellow time, and green minimum green times are specified. The yellow time being, the all red time being the time from one phase running to the next phase running, so that the car can clear before the next conflicting green can run.
Thank you. So Maria,
Yes.
you would like to show the squeaky wheel approach in the Netherlands?
Yeah, I'm going to share.
Stop sharing.
Oh, it's going to stop sharing? Okay.
Please.
Here's an interactive map of Utrecht where people can complain about an intersection, and then you can see how many complaints there for a certain area are and which intersection you have a complaint about. And if you go there, you can still see as a manager what kind of complaint there is. I've tried to click on one. This is
a public website?
It's a public website. Here you can say kind of voetganger fiets, so a pedestrian, bicycle or car. I'm going to choose this bicycle. From which direction? I'm going from the Verlengde Vleutelsweg to this direction. And I'm going to the Vethornplaats, and no intersection controls needed here. Or you can use them for only a part of the day, or they're really needed here. Or it's you have if you turn right for cyclists, I wanted that because I can easily turn right without any problems, and or a different problem, and you can describe here and your name, mail address, and then you can explain what is happening here.
Oh.
So create a squeaky wheel, and then you can say, well, I've got a list of complaints. Which one is the highest complaint? I'm going to start over there. So this is the way.
I love it. I think our system would fall over in the first day, but yeah.
Yes, you have to know what you have to do, and also if the people start complaining, explain what's happening here. So every now and then.
Thank you. Is there any more questions?
I can maybe add, in Germany we have a similar system, not for traffic. I'm not aware of traffic lights specifically, but for cyclist traffic. They introduced this kind of approach some years ago. And I think it's a big challenge for the authority. Well, it's an opportunity because they get information they otherwise wouldn't get. So in a way, it's a nice quality management system, but the management part is kind of challenging. So how to set the priorities, that's a big challenge as well. In Germany, we tried to introduce a systematic quality management for traffic signals some years ago in the guidelines, and it was a big discussion because all the authorities said, well, we don't have the resources for that. And my opinion is that for some reason, it's the same issue you mentioned as in Australia, Daniel, that the authorities are busy dealing with those citizen demands and this squeaky wheel approach, and therefore they don't have the time to do it systematically. So it is a challenge. And maybe one question, if I'm not mistaken, on your you showed a phasing plan, and there was no right turn phase. Do you have right turn on red, or how do you deal with the right turns in Australia?
All right, I'll load up that plan again. I'll share my screen just to make sure I'm on the right page. Was it this one here?
Still busy.
Am I good?
No. Yes, exactly. And if I'm not mistaken...
So in Australia, signal groups 3 and 4 are the right turners. So in A phase, this one...
Sorry, the left turns. The left turn was missing. That's just because you don't show them, or...
they're not signalized. So we're assumed in Australia that signal group 1, when the through movement here on signal group 1 goes, the pedestrian can also run, but they can left turn over the pedestrians in terms of filtering with the pedestrians.
So that's the standard situation.
It's evolving. In Queensland, they're requiring pedestrian protection now. So we'd actually have a left turn, red arrow would come up for the walk component of the pedestrian crossing, and then the left turn red arrow would drop off, go blank, and then showing that vehicles can proceed left as long as they give way to any remaining pedestrians. But the majority of the time, our left turn movements are not controlled, understanding that we drive on the left-hand side, so just making a left-hand turn, we don't usually control it via traffic signals. It's
a mixed lane with the through traffic, or
yes,
it
is a shared lane. It is a shared lane for a lot of intersections, but there's a lot of intersections where it's a dedicated left turn lane as well. But on a smaller urban intersection, it would be a shared through and left lane.
Yeah, okay, because that's for coordination. It's also a challenge. You have to judge how much time you need for the left turn traffic to move on so that the platoon can pass this intersection if it's a shared lane. So that's one of the issues in Germany, where you have always to judge how much time, advance time, do you give to the left turning traffic, or in Germany it would be right turning traffic. Yeah.
To remove the residual queue that's sitting there at the start of the signals, yes, big time. Yes. Yeah.
Thank you.
Thank you.
There's another question in the chat from Abdu. What major hurdles other than the operation of controllers do you foresee in moving from the current stage-based approach in streams towards a group-based approach?
Okay, so it's in the Australian context, the Department of Transport and Main Roads Queensland are currently in the trial of SWACO controllers. A lot of what I've presented on is what's actually happening, but we're in the process. I think we've got like 7 or 8 of them out there in the field right now, and they are movement-based controllers. So we're moving towards a SWACO-based controller with streams still controlling the traffic signals. I'm not sure how this is going to evolve over time, but at the moment, we'll be able to view and operate the SWACO type controller through streams. The biggest hurdle has been that the Australian standards, AS 2144, was very prescriptive. I know elements of it. I wouldn't say I know the whole lot of it by any stretch, but it had things like, I want to make sure that the wire is blue colored. Not that the wire must carry 5 volts at 2 amps. It has to be a blue wire that carries 5 volts at 2 amps. This is just an analogy. And it meant that overseas controllers that had a brown wire that carried 5 volts, 2 amps, were not allowed because they didn't meet the Australian standards. Our standards were very prescriptive and written in such a way that it made it extremely hard for overseas controllers to come in. And it's only the very large road authorities that can take the risk of trying a non-Australian standard controller because they're wearing quite a lot of risk. They're going to make sure it meets all our electrical safety requirements and that it's going to function correctly on the street. So that stopped the overseas controllers and all the different manufacturers from selling their gear inside Australia for a very long time. We had Eclipse, QTC, and Aldridge selling their controllers in Australia in-house, grown. They were built here. They spent a long time working in it. But now we're starting to see Queensland has looked beyond that and they're trialing new controllers. It'd be very interesting to see where that goes. There's a lot of different things that it'll be hard for us to get there in a way because we're so being used to the same way of operating. Old boss of mine, who's now retired, he had a guide to traffic engineering practices from Austroads, and it was printed in 1970. And it wasn't dramatically different besides, you know, updated fonts and printed in a better way. The content wasn't dramatically different. Not much has changed in a long time here for the core basics. And I think that'll be the biggest hurdle is re-educating all the practitioners on this newer way of doing things. I'm excited for it. I can't wait for it. I think there's a lot of potential, but that's probably going to be the hardest part is the people part.
Okay, Daniel, can I have a question for you?
Yeah.
You mentioned a term called route manager, I think in slide number 7. Mm-hmm. Can you talk a little bit more about this role of this route manager? So you have this kind of position or, let's say, task for every city, or it is customized for different cities? Route manager.
Yeah, so in Australia, because each state does things a little bit differently, we're working towards operating the same, but we are individual beasts. Over in Western Australia, they've got this concept of the route manager. It's something that's been brought in by the manager there, the executive director for the road operations group. It was his, Tony Earl is a gentleman's name. It was his, he brought it in. It was his idea. He used to work for Transport for London, so I'm sure he's brought the idea from there. The idea being that this person or this position for this particular area is responsible for that route. Everything and anything to do along that route, they're meant to be across and have an understanding of. So they basically didn't want there's a saying that when you're a hammer, everything looks like a nail. So when you're a traffic signal engineer, all you try and do to fix the corridor is readjust the timings and play with the traffic signals. But in reality, it may be 200 meters away from the traffic signals, there's a problem there that you should really look at. Or downstream from the traffic signals, it's when the traffic leaves that there's a roundabout there that's causing all the problems along the corridor. And the idea of the route manager was to stop being myopic about traffic signals and look across the broader traffic engineering discipline to come up with an idea to solve the corridor, as well as look at the alternate corridors. And that's where the Victoria movement in place has evolved even more to, where they're looking at the entire network and saying, well, I can't get trucks to work down this corridor. We're going to make the corridor one to the parallel one. That's now the truck corridor. We're going to make it work for them. We're going to have larger cycle lengths with larger minimum green times, so give time for trucks to start. No stops, so have bigger green bands, but on this corridor, we're going to have shorter cycle lengths because it's an active transport corridor. So did that answer help out?
Yeah. Then how to select these roads? I mean, let's say critical roads, right? You cannot put one person for every route. You need to select some critical ones. So what is the philosophy behind selecting these roads?
It's how much money I can get from my boss is essentially it. So I'm given staff, so many staff members, and I've got an area of 20 corridors. I've got 2 staff members. You each get 10. Essentially, it's probably no more logical than that. There are obviously the more systematic approach we take, the better reporting and stuff like that, the more we can go, see, boss, we did this review. Can I have more money to get more staff to do more reviews? And that's what we try and do. But a lot of it does come down to your available resources, funding and stuff like that. But yes, it's definitely not one person for one route. I think they split the city. I think they've got I think it's 6 or 8 route managers for all of Western Australia or something like that. But it essentially just comes down to the resourcing that your individual road agency has and the priority they put on this type of work.
Okay, thank you.
Okay, any other questions to Daniel? If no, we would like to continue to the discussion part. Thank you, Daniel, for your great presentation. So let's move to the discussion as a whole workshop. So today we have the 3 presentations from Japan, Netherlands, and the Australia. And in the previous workshop, we had a case of China, the USA, and Germany, and Switzerland. So we can start from any point regarding the discussion of what is the most important for signal coordination, or what are the challenges, or something like that.
I actually have a common question for all the 3 speakers. This question was asked to Maria before. I want to know, do you have sort of a standard procedure to determine when and where to implement signal coordination? Especially, for example, if it is decided that, okay, this corridor should be coordinated, then what type of coordination should be used? Is it, can I say, recommended in the guidelines, or it is actually decided by different consulting companies or road authorities? So in Japan, in Australia, and of course in the Netherlands, Maria, if you would like to say more, explain more, it's okay. So can you understand the question? Yes, yes.
Okay, from the Japanese situations, actually, I think I'm not sure. I don't have the concrete idea for that question. But in my understandings, that as the previous quick question respond to the quick question, as I mentioned, that there exists even a few numbers, but some traffic engineers inside the police agency. And they are always have a responsibility of their road traffic management. Therefore, if they find the coordination is essential for some road, then they may ask to the supporting industry companies to make some survey and the checking and the effectiveness of the efficiency of the introduction of the coordination. Then they may take some coordination. And what type of the coordination is also related to the budget limitation and so on. And if the even unconnected the fixed time the controller, but they may adjust the timing of the start of the greens and so on. Then they can have some coordinated situations. But for respond to the traffic demand change, maybe they need to have some investment to have detectors to measure the traffic situation and so on. Therefore, maybe another type of the decision required, not only introduction of the coordination, but to enhance the connected, decentralized control systems is the another decision making, I think.
So how is the public complaints, can I say, work in this kind of decision? You know, in our case, we, as Maria explained, with that website, so if we receive a lot of public complaints for some routes or some intersections, then the road authorities have to respond. In such a case, they put some resource on that. So is this happening in Japan?
I think yes, because the police agency also have a kind of such a open box to accept any comments, not only for the traffic, but any activities and of the for the police agency activities, and also through some political the power requested, then. Therefore, always the policy agencies are trying to select which policy should be applied. Maybe that's kind of the major role of them. But I think there is no very clear the standards or kind of guidelines to be followed. Therefore, the managers of those sections have a very big responsibility on that. That's my opinion.
It's a resource driven. It's some money you can do it. You have no money, you can.
No.
Thank you.
Can I add something to my remark earlier?
Yeah, sure.
When you have a certain road and it should be improved and there's money for it, for instance, the road at this Delft I've shown, this is a provincial road and the provinces said we have money to improve the traffic situation at this road. Then they write a tender that they say, well, this is our policy and this should be what the control should lead to. And then you have companies and they say, well, this is our price and this is our method. And then some certain consultancy wins this tender. So the reason there's inflow rather than top track fast on this route is because Dinnick won the tender instead of Vialis. While in Almere, Vialis won the tender for the inflow and the top track fast method in Almere. So there's also the provinces or the municipalities decide on the policies, and well, there are consultancies that can try to give a method that can make these policies come true.
Okay. Thank you.
So from the Australian context, so for us, in terms of we basically do have coordination across everything that should be coordination. It's just to what degree of quality it is. So when we do put in a new set of signals, in theory, we are putting in coordination plans and setting it up so it can be coordinated. But it just comes back to how much the resource leveling that you have. So in some of the smaller jurisdictions, I worked in Canberra, Roads ACT, which was the Australian Capital Territory. We only had about 300 sets of traffic signals in that territory, and there's two of us. There was two people to manage all those traffic signals and everything else. So you're a jack of all trades. We're responsible for maintenance contracts. Sorry, in theory, there was four of us, but two traffic engineers, a drafter and sort of a communications person who looked after some of the network stuff. But that was it. So we were responsible for members of public concerns, doing coordination reviews, upgrades, controller replacements, everything, personality generation, everything. So it just comes down to your resources. We have the tools across the majority of Australia. New intersections are required to be connected to the centralized traffic signal system generally. And that's a pretty firm requirement. There's a couple of local areas that don't enforce that. More over time, they weren't originally, and they're playing catch up. But it generally comes down to the quality of it is determined by resourcing. So very different from the Netherlands in terms of if a consultant comes in and says, let's try a different traffic signal system, it's a big ask for us in terms of, well, you need to bring in a lot of different stuff. We've kind of said this is the traffic signal systems, and consultants can work and say they'll help out with the coordination using the existing tools.
Following your answer, you explained the clustering analysis when you decide the signal groups that you should coordinate. So this is your kind of procedure of your company, or it is general in Australia?
So back in 2012, I did a paper with a colleague of mine on using this algorithm for the first time we used it. How widely it's been taken up, I'm not sure, but I know there's places in Queensland. Whenever I do my coordination reviews for helping out people of Queensland, I definitely use that methodology. It takes a bit of work to get the data together, but we're getting better and better about getting that data together. Other states and territories, I'm not sure how much. I do know that Add Insight, which does the travel time analysis from Bluetooth readers, it uses cluster analysis. The developer of that was actually at that presentation back in 2012. And he said, oh, that's a great idea of identifying normal traffic patterns, and embedded that into that. So I'd honestly say it's not super widespread, but I prefer it as a mathematical tool for working out the traffic patterns, as opposed to what I used to do, which was just get a feel for the corridor, look at volume patterns and stuff like that. So just another tool in the case.
That's good. Thank you.
Okay. Any other point of the discussion? Yeah, I would like to discuss about how to evaluate the signal coordination, since in the previous workshop we also had this kind of discussion, and what kind of performance indices are used and how frequently the coordinations are reviewed or something like that. And I heard most of the countries in the previous workshop had a limitation of the resources. That's why they evaluate one time at least, and not so frequent reviewing of the changing, the updating the fixed the coordination systems or something like that. So I would like to have the opinions on this time.
Okay. From me, from the Japanese situations, and also my personal opinion, I think that's the big issue in Japan. As you may see, that the too many number of the signals we have, and maybe to also add the words on the Maria's the comments questions. I think once in Japan we try to install the signals because the distance to the nearby signal is not so far. Therefore, almost always we try to coordinate to set the parameters once. On the other hand, as mentioned, that the big issue is how to maintain the coordination settings. Sometimes the traffic demand will drastically change because of some land developments change or any other those socio-economical changes. On the other hand, we don't have any good observation tools to evaluate the performance. Therefore, these days, also for that context, I try to utilize the probe informations is one big issue worldwide. The nationwidely, including all the industry companies, and they are now doing the intensive work, try to utilize the probe information and to evaluate the performance rather regularly compared with the past. But still, it's a kind of under the study stage, and but I hope in near future, in a few years, I think we would have some good system to evaluate the performance of such a fixed time signal controllers with the probe informations, and then we would have a rather regular the updating of their parameters to have a rather better coordination. That's my opinion. Thank you.
Shall I continue? We have, of course, the coordinated direction, and then you can say, well, we want to limit the number of stops because it's important for the environment. It's less polluting when you can continue, especially for trucks. This is important. And but then sometimes you have to, if you want to make a platoon, you have to gather at the first intersection of arterial the vehicles, so they might experience more delay at the beginning to make sure they will continue in one flow. So you have to balance between the delay and the number of stops. And of course, you have also the crossing directions. And if you have an arterial within a part of the urban environment, then you have much crossing traffic with pedestrians and cyclists, and also car traffic not on a coordinated direction. And then you have to balance between the maximum waiting times for these directions versus the coordination on the main direction. So it's always balancing between delays and number of stops on the coordinated directions.
May I ask what is the maximum waiting time? I mean, what is the limit for waiting time in your guideline or in practice?
Well, we try to keep the cycle time at maximum of 120 seconds. So I would not.
For vehicles, right? For vehicles, not for pedestrians.
No, the cycle time, the complete cycle time for all directions. So you have also part of them is green time, so at maximum. But well, if it's really busy, we try to have an extra phase for the cyclists. But okay, of course, this will hamper the coordination in the main direction.
Thank you.
When you check the number of stops, do you conduct a field survey or you evaluate basically based on the detector information?
Detector information. We have a dashboard that shows how well the intersection control works. Therefore, I was curious. I'd ask this question.
Thank you.
More and more information is available, and so more and more dashboards become available as well to show all this information, to make have an impression how it works, because you can show the information, but then not certain is your policy working. So you have to match what you want with all the information you got, exactly as Daniel said.
Just on that note, with the 120-second cycle length, how large are some of your intersections? How complicated? Is that even if you've got, say, a 6-lane intersection with multiple right turns and things like that? Are you still keeping to that one?
I don't know. I do not think we have 6-lane intersections, but are a bit smaller. Okay, 150 might happen as well, but not much larger. And then it's not really an intersection anymore, but we mostly do coordination on the urban intersection control, what I've discussed here. I do not know whether on freeways we try to avoid to have intersections, but also we have, of course, that you have to manage that when you want to move on the freeway from the urban arterial, there is an intersection. They might have a higher cycle time, but then you have only cars, and it's not the situation that you have cyclists and pedestrians, because you have to move on the freeway, and then you won't have any cyclists near.
Oh, interesting. So in terms of measurement in the Australian context, I think one thing we've done poorly in the Australian context is we do a lot of measurement up and down the main arterial, but we're not very good at side streets or coming from crossroads and things like that. We have I'm working with a university at the moment. We're trying to do a better Q estimation model for from detector information, overlaying that with travel time information, and basically seeing what we can do to come up with a better Q estimation model from the detectors that we have, because I find that for some of the coordination work that I've done, and I know some of the other practitioners, if we just make the cycle length larger, the travel time improves because we have one big massive green band, but we don't measure the side street delay. We don't measure accurately what's happening on the side streets. And because of that, I think in some jurisdictions, it's, for lack of a better word, people are getting lazier and making larger cycle lengths because the main metric, which is the travel time along that corridor, is improving. So where's the problem? So I think, to me, that's a really big thing that I'd like to see done better, is a really good metric for side streets, but unfortunately I haven't come across one that works really well because of how far that queue length is. Whilst we can figure out that 100 cars went across from the side street, the delay of each of those ones, I don't think we have anything accurate enough, nor the queue length estimation on the side street throughout the day to have an accurate prediction in our world. But that's something I'd like to see so that we can aim to optimize both the arterial corridor as well as balancing that across the side street delay. And that's something that transit does really well, because you can put in all the different optimization parameters that you want, but it just takes a hell of a lot of work to get a calibrated transit model. Assuming that the network doesn't develop, then, you know, new housing development, and all of a sudden your model is not calibrated, so it's worthless. So, yeah.
I know there have been research in the Netherlands on the Field Operational Test Integrated Network Management Amsterdam, that they do have a model made for a Q estimator. Maybe it helps to have this in information. I have a TRB. I don't know this particular paper by heart, but it must be in there because I know this Praktijkproef Amsterdam, the Field Operational Test, had a Q estimator. But I'm not certain, but I will share it anyway.
Thank you very much. Appreciate that.
Yeah, this part is also when you have a major road, freeway, and you have people entering it. You have that you have a traffic signal to let them in on the freeway, and how does this work together with a network in Amsterdam itself. So I hope that this part, if it isn't, because I only have Googled for the Google Scholar of the Praktijkproef Amsterdam, because I know that I have a Q estimator in there. But if it isn't, please let me know.
Very good. I remember that last time you said you may be interested with the third book, which will be on the new signal control in the context of emerging technologies. So if we are going to have the third book, are you interested of being a contributor of this book, either an editor or author?
Yes, I would be interested. So keep me in the lead. I do not know when should the book be written. The parts be written.
We haven't a concrete plan for that yet.
Okay.
But it should be, I think, scheduled very soon in this year or next year. Now, okay. Most of the time, we're working on the second book, led by Professor Zongqian. Yeah. But I think we should start the third book, at least to consider the
I will. Yeah.
So if you're interested, we will keep in touch.
Yeah, please do.
Yes, since we know that there are many new things happening in the Netherlands always in the field of transportation, right? So we look forward to have your contribution for the third book.
Yeah.
Thank you. Same to Daniel. If you are interested with that, please let me know. You can write, for example, a chapter for the case in Australia, or you have a specific topic. That's also welcome. And I think you can, of course, you can co-author with Ashish, whoever you like, right?
Yeah, no, thank you very much. I'll definitely, I think Ashish and I will have a chat about that for sure.
Okay.
Keen to.
Thank you so much. Yes. And so you can lead the third book. So really, I'm serious. We can do this third book at simultaneously with the second book. Okay, let's talk about this later.
Okay, later. Okay. So I wish to have some opinions or questions or any ideas from the audience. If you have any, please don't hesitate to talk.
Okay, I like to give us my opinion on the signal coordination. I think back to a kind of evaluations or performance confirmation, I think. To considering about the isolated a single intersection, then the performance could be rather easy to be observed with some the infrastructure detectors, or also combined with the vehicle movement. On the other hand, to evaluate a kind of a coordination effect, I think including the different users and maybe the setting of the coordination parameters is a kind of based on some assumptions. But the performance evaluation, I think it's rather difficult, I think, because of the many users, like large heavy-duty trucks or the personal cars. Also, they have a different speed levels, and also including the bicyclists and so on, as you discussed today. Therefore, how to evaluate the coordination and discuss about the different direction users is a kind of a big challenge, I think. So maybe to discuss about the network-wide traffic management, and actually considering about the real-time, the dynamic issues, then we are facing with a very, very big challenge because of the changing the parameter dynamically is based on the unknown future issues. And the reality is only the observable after the performance conducted. Therefore, what is the best or better strategy to make a kind of such a signal control in area-wide, or even considering about the coordinations? That's just how to say, I'm thinking about such kind of difficult questions. So I just give just open question to all of you.
So yeah, I definitely think that's a very complicated one. For a long time, I kept trying to come up with my own sort of algorithm and a better way of coordinating at a network-wide level, how to do a lot of stuff. And I think where I've landed, Transmax itself, it's a tech company that does a lot of traffic engineering software stuff. Well, everything I've said today is as a traffic engineer, but what I think we need is, I almost see it as a machine learning type of style. I think there's a pattern and there's something out there that could come up with a better timing parameters that I think is beyond the scope of something that I can do, traffic engineering practitioners. And that's why I think we almost need to feed into a system as many different data points as we can, and let it see if there's any correlation, using machine learning to come up with a network algorithm that's going to work better. I think that's where we need to go as an industry. I think we're at the limitations. A lot of my work is manual and through experience and things like that. And I don't think I should be doing that job now at all. I think the Netherlands probably has the best opportunity for this with the number of detectors and inputs they've got. And they're probably halfway there from the looks of it. But I think that's where bringing in things like rain patterns, travel times, detector, very isolated microscopic model stuff, as well as macroscopic. You know, today is the day before a public holiday and it's a long weekend, so we know that traffic always leaves earlier. That type of stuff. There's a lot of stuff that working in a traffic management center that you come to learn. A little bit of rain doesn't affect, I've read a study that a little bit of rain doesn't affect the number of people using cyclists, but a lot of rain and people don't ride, so they drive, which increases the traffic a lot. So a little bit of rain doesn't matter. A lot of rain completely kills the network. There's things like that, metrics that need to come into a system to work on that prediction stuff that is beyond my brain. But I think my 2 cents is where we need to go as an industry.
I agree. We do machine learning, and I'm starting now projects with artificial intelligence for traffic control, not only for assessing, but also doing the control itself. But the most important question is, what is your policy? If you don't have a clear policy, you do not know what is optimum. You have to explain that to the machine learning or reinforcement learning. This is good. So what is good? What improves the livability of our cities? This is the main question. If you can't answer that question, you can do any technique you want, but you will not have optimum control. So, for instance, take the rain. We have rain sensors for cyclists. If it's raining, they get more priority. But why don't they get a priority when it's sunny? If you want to improve cycling. For instance, when last year it was a very hot day, and I was burning away at the intersection. We're not used to 40 degrees Celsius here in the Netherlands. It's not pleasant because we have a high humidity, so it's really hot when it's 40 degrees. And I rather had priority at that certain moment than at the rain sensor. I do not mind it, it's a bit of rain or even a lot of rain. I have my rain gear, so... What does improve the livability of your city? When do people take the bike? They do not take the bike, don't take the bike because it rains, but they don't take the bike if there's not good infrastructure for the bicycle. And this infrastructure is not only the cycle path, but also what do you do at intersections? So policy first and then the techniques.
And I think that's where Department of Transport in Victoria, in Australia, Victoria, the movement in place concept where they've split out each corridor and said, this time of day, this class of vehicle has priority through here. I think they've answered that part in a very structured way. And so they're ready for your output of the machine learning. So they've done that really well, which is really defendable. And they've said, yes, pedestrians have priority, but they aren't dynamically reacting to things like weather or anything like that by any stretch. So having a dynamic one reacting would be the next step.
Thank you.
Thank you for your response. It's very. I totally agree with both of you the comments, and also I like to give some additional the issues that the. Yes, I also totally agree with applying the machine learning and also the big data to predict the future or near future. But if the system, the traffic, road traffic system comes to be rather near saturated situation, then the system performance, the stability comes to be very, very unstable. So that because the prediction should not be very precise. Always we have some the unexpected the fluctuations, and which may lead to the start of the congestion, oversaturation, and so on. Therefore, maybe for example, in the case of the such a congested urban area like Tokyo, I think the predictability would be some level limited. Therefore, a kind of a reactive or a kind of some additional the technology or the function or the policy is required for such a very congested, dense traffic situations. Thank you.
Thank you. Thank you for your very fruitful discussions. And although we would like to continue, but the time is almost up. So if you would like to add just a short comment, you can, but if not, we would like to.
Well, one remark on that, because I think also informing the public in which time they should leave their house is important, because if you leave somewhat earlier or somewhat later, you might have a better spread of the traffic over the day. And also we have done some research about the combination of routing and intersection control, which is the way you can spread the traffic more evenly over the intersections. That is also might be a way to go.
my final 2 cents on that one as well. I was fascinated to see the red wave from the presentation, from the last presentation in China. I think what the ultimate may be is that we know the critical capacity of our network, of a area, and we just simply can't let more cars in once we reach that critical capacity. And if we control the entry of vehicles into a cordon zone, control them through that, and then almost like at a nightclub, 1 person in, 1 person out type style, I think you might need an element of that, and definitely travel demand management. We had the Commonwealth Games on the Gold Coast in 2018. Travel demand management managed to reduce the background traffic significantly, crazy, almost too well. They did an absolutely excellent job, and I think both informing the public of when you can travel and controlling that critical density.
Indeed, also when gating for the urban area for a network is important, and then you can have the MFD, the macroscopic fundamental diagram, to see what happens at your intersection, whether you're nearing the congested branch. Then you know we should stop adding more traffic. It's also part of research.
Thank you so much. I think a lot of important ideas and the keywords were raised in this discussion. Thank you so much. So I would like to move to the closing address by Professor Kishan Tan.
Okay, just very short closing. I would like to thank you, all the speakers, for your excellent presentations. I understand that you spend a lot of time for it, especially for Daniel. Today is your holiday, actually, right? Thank you so much for joining us and sharing. So I would like to ask you all to send me your slides, and I will put those slides together with our recorded video at the website of 62. At the same time, we want to make this video open to the public. So this time we might upload them to, for example, YouTube, if you agree. Okay, then your research, your ideas, your thoughts will be known by more people. Today the number of participants is very limited, but I think via the video, more people can know about our discussions today and also your presentations. So thank you very much again. I have nothing else to say, but I hope that you can still join us for the third one. Although it is still being planned, no exact date and time is decided, but I will let you know afterwards. And finally, I would like to thank all the audience for attending this workshop. Thank you so much for your questions and joining the discussions. Thank you. That's all from me.
Thank you. Thank you for all of you. And
thank you so much.
Thank you. I enjoyed the presentation.
Thank you.
Bye.
Bye, everybody.
Thank you very much.
Bye.
Cheers, guys.